Hi, this is Mr. Mulick for KMT Chemistry. This is a review of the bonding unit. You should make sure you have your periodic table and any notes that you need handy. Be prepared to stop this video a number of times. I'm going to go through it kind of quickly in case you need to write anything down. So for bonding, there are three types of bonding that we talk about. The first I'm going to talk about is ionic bonding. Ionic bonding takes place when two elements are going to combine through the transfer of electrons. Now, the easiest way to spot an ionic compound is when the electronegativity difference between those two elements is greater than 1.7, although there are a couple exceptions. One case is hydrogen fluoride. The electronegativity difference is actually 1.9, even though it's a covalent compound. So the much better way to determine if your compound is ionic is if you have a metal bonded with a nonmetal. Of course, there are a couple exceptions to that as well, namely the ammonium cation. In an ionic compound, the metals are the losers. They lose electrons and become cations, or positively charged ions. The nonmetals gain electrons and become anions, or negatively charged ions. As a brief checkpoint, you should be able to identify one of these four compounds as ionic. Take a moment and do so now. Excellent. Turned out that aluminum fluoride, AlF3, is your ionic compound. When a metal and a nonmetal combine to form an ionic compound, typically they combine in certain ratios determined by how many electrons each atom has, because you want to maintain neutrality. So the best way to determine what the ionic formula is for a binary compound, first you need to figure out the charge on your metal. For group 1 and group 2, the charges are +1 and +2 always, respectively. And for transition metals found in between groups 3 and 12 in your periodic table, for some there are multiple charges available, so you're going to want to use your periodic table. Unfortunately, there is no general trend with all the transition metals. Many of them have the +2 charge, but not all, so use your reference tables when at all possible. To determine the charge on the nonmetal, take the number of valence electrons in that atom and subtract 8. After you determine the charge on your metal and your nonmetal, you use the swap rule to determine the ratio of cation to anion that will give you a neutral compound. Make sure you always report your ratios in the lowest terms. Here I've included two examples that I'll go through really quickly: lithium nitride and calcium oxide. First step is to figure out your symbols and figure out what your charges are for each of your metals and nonmetals. Lithium being group 1 is a +1, calcium being group 2 is a +2. For nitrogen and oxygen, we have shown -3 and -2 respectively. Now, in using the swap rule, you take the numerical value of the charge and you move it down to the subscript position on the other element as shown here. So your formulas will end up being lithium nitride Li3N and calcium oxide Ca2O2. But this is not in lowest terms for calcium oxide, so make sure you reduce your ratios to the simplest whole number. When naming ionic compounds, there are three general categories that all ionic compounds fall into that you need to know about. The first is the simplest: binary ionic compounds, one metal, one nonmetal. For the metal, leave the name as it is. For the nonmetal, change the ending of the element to IDE. An example of this is strontium bromide, shown on the right. This is a binary ionic compound because there is one metal element and one nonmetal element, even though there are three atoms in the formula. The second type are compounds that have polyatomic ions in them. These have more than two elements in the compound. The easiest way to name these is to use table E to figure out what the name and the charge of the polyatomic ion given is. Your example here is sodium phosphate. PO4 is your phosphate anion, shown on table E of your reference tables, has a -3 charge. An interesting side note: these compounds that have polyatomic ions display both covalent and ionic bonding in their compounds. The dimercury ion is an example of a cationic polyatomic ion. These are covalently bonded molecules that as a whole have an ionic charge. The third case is any ionic compound that follows the stock system, meaning that it is using a metal that has multiple charges listed on the periodic table. Typically, these are your transition metals between groups 3 and 12. Whenever given a metal that has multiple charges, you must use Roman numerals to indicate the charge of that metal, numerical charge. A good example here is iron 3 chloride. Looking at the periodic table, iron can be a possible +2 or +3. Since chlorine is a -1 and there are 3 of them, iron must be a +3 to maintain neutrality, hence iron 3 chloride. Properties. All of the properties of ionic compounds come from the structure of the ionic compound. Ionic compounds are alternating ions. You see cations surrounded by anions surrounded by cations in all three dimensions as shown here. This is a tightly packed, heavily attracted, rigid structure. This high attraction of the ions leads to the high melting point and boiling point of ionic compounds and very hard crystals. Even though the crystals are hard, however, they are also brittle. As a crystal is struck, the ions can line up in a repulsive manner, making the crystal fall apart very easily. Many ionic compounds also dissolve in water. When they do, the ions are allowed to freely move, which causes electrical conductivity. Ionic compounds will also conduct in the liquid phase because ions, again, are mobile. Covalent bonding, unlike ionic, instead of transfer, you have sharing of electrons. The reasoning being that neither element wants to lose electrons because the electronegativity and the ionization energy are both too high to lose electrons. The easiest way to recognize a covalent compound is that the electronegativity difference is less than 1.7. Again, there are exceptions like hydrogen fluoride where the difference is 1.9. To get around the exceptions, look for compounds that do not have metals. However, there are exceptions here as well, ammonium being a polyatomic ion. Even though elements in covalent compounds share electrons, the sharing does not have to be equal. You can have unequal sharing as well, equal sharing being called a nonpolar bond, where the electrons spend equal amounts of time on average with both of the elements. Unequal sharing called a polar bond, where the electrons will spend more time around one element than the other. Using this information, you should be able to identify a covalent compound. Take a second and do so now. Good. Sulfur dioxide is the covalent compound here. When representing covalent compounds, Lewis dot structures are drawn. To draw a Lewis dot structure, first you have to be given a formula. Your first step is to figure out how many bonds each element wants to make. The way to do this is to subtract the number of valence electrons from 8. To give you the number of bonds. For carbon, you see 4 bonds. For chlorine, 1 bond. Hydrogen is an exception to this rule because it only makes 1 bond, needing only 1 electron to satisfy its duet, since there are only 2 electrons in the first shell. The next step is to draw all the atoms in your molecule with valence electrons, as seen here. Next, start pairing up single electrons to make pairs to satisfy the octet rule for all atoms present. After doing this, you may want to redraw the structure a little more aesthetically, as shown here. Don't forget your lone pairs. Every Lewis dot structure must show the octet rule being satisfied for all elements. Lines can be drawn instead of pairs for bonded pairs only. A second example is carbon dioxide. As you can see, carbon needs to make 4 bonds, oxygen, each one needs to make 2 bonds. So the first set of bonds you make are shown here. However, the octet rule is not satisfied for any of the atoms present, so sometimes when drawing a molecule, you'll need to make multiple bonds. Double and even triple bonds are possible, but don't go any higher than a triple bond. There are 2 considerations for polarity for each covalent compound. First, the bond polarity. Bond polarity is determined by the relative electronegativities of the atoms in a given bond. There are 2 types of bonds, polar bonds and nonpolar bonds, and electronegativity tells the difference. If the difference in electronegativity between your 2 atoms is 0, this is a nonpolar bond. This means that the electrons are equally shared between the 2 atoms and spend an equal amount of time between one and the other. For any other difference greater than 0, any difference at all, the bond is considered polar. This means that the electrons will spend more time on one element than the other, giving you a partial charge. Not as much as you see in an ionic compound, but a partial charge. Molecular polarity considers the distribution of charge over a molecule and considers all bonds together. One way to do so is to find the centers of the slight positive and the slight negative averaged out over the whole molecule, or much easier, the rule SNAP. Symmetrical molecules are nonpolar, asymmetrical molecules are polar. Any line of asymmetry that can be drawn down a bond makes the molecule polar. Here are some examples of molecules and their bond and molecular polarities. Hydrogen you see has a nonpolar bond and is a nonpolar molecule. Carbon dioxide has very polar bonds. However, since the molecule is symmetrical, the pole towards one end balances out the pole towards the other, leading to a nonpolar molecule. Fluoromethane, shown on the bottom, has polar bonds and is a polar molecule as well. To name covalent compounds, use prefixes to indicate how many of each atom is present. Here's a table that shows the prefixes for 1 through 10. Put this prefix in front, that lets you know how many should be in that molecule. For the second element, you change the ending to "ide." When listing elements in a covalent compound, the lower electronegativity goes first, followed by the higher electronegativity. There is a slight exception to this rule. If there's only one of the first element, do not use any prefix. A good example of this is carbon dioxide or carbon monoxide. It's not called monocarbon monoxide. You drop the mono prefix for the first element. Here are 3 examples of covalent compounds going between name and formula. Properties of covalent compounds are basically the exact opposite of ionic compounds. Again, they stem from the structure. Instead of a dense network of pluses and minuses, these are discrete molecules that get together in certain ratios to satisfy the octet rule. Once the octet rule is satisfied, a given element has no reason to interact with any other elements around it. This will lead to a low melting point, a low boiling point. Most covalent compounds are gases at room temperature. Think about methane, hydrogen, oxygen, nitrogen, carbon dioxide. The ones that are not gases at room temperature are typically very soft solids. Most covalent compounds do not dissolve in water, and because they do not interact with each other and do not have mobile charges, they are insulators of electricity. They're also insulators of heat. There are some special cases to consider with covalent compounds. Allotropes are different structural forms of the same element. Because of their different structure, each allotrope has its own properties. Examples: ozone, O3, and oxygen, O2. Diamond, graphite, and fullerene are all three forms of carbon with very different properties. Network bonding is when you have a compound or an element where the atoms are combined in a continuous network of covalent bonds. There is essentially one humongous molecule in one big crystal. This dense web of bonds creates an extremely hard and high melting substance that doesn't dissolve in water. Great examples of network bonding are diamond, boron nitride, or sand. Metallic bonding is defined as mobile cations immersed in a sea of electrons. To recognize a metallic bond, you're talking about a substance that only contains metals. Metals only. The low ionization energy of metals causes them to release valence electrons, which will lead to properties such as being malleable and ductile, and having high melting point and boiling point. The mutual attraction for the electrons keeps them together. This mutual attraction also leads to the high melting point and boiling point. There is one exception to this, that mercury is a liquid at room temperature. That's bonding. Feel free to scroll back through this video, pause, and copy. Happy studying. Thanks for watching.